Should I bring my slide?
Good afternoon. Welcome you all in today's afternoon session by Professor J R Kayal. We thank you, sir, for accepting our invitation to ignite young minds of India by sharing your experience and expertise in the field of geoscience. Every year, BSc and MSc students get hands-on training in the CSIR labs, but this year it was not possible. Therefore, DG CSIR Dr. Shekhar C. Mande sir has conceptualized the idea of online summer research training program under able leadership of Dr. G.N. Shastri, Director CSIR NIST. It is going on, where students get chance to hear from eminent scientists like you and get updated about the theory, utility, and importance of modern high-end instruments. They are able to enrich themselves without coming out from their home. Total 16,000 applications are received and all are given opportunity to participate. Sir, your lecture will be live telecasted over the 3 platforms, MS Teams, Facebook, and YouTube. With this brief introduction about SRTP, once again I welcome you and handing over to our director, sir. Sir.
Good afternoon. It's indeed with a great pleasure that I introduce Professor J R Kayal, who is a world-renowned expert in exploration, geophysics, and earthquake seismology. Professor Kayal has more than 5 decades of experience. I feel that his experience is probably double the age of the average participant in today's seminar. Thank you very much, sir, for inspiring us. And soon after he got his MSc Tech in Applied Geophysics from Indian School of Mines, Dhanbad in 1969, he took up the position in ONGC and worked in that for a brief period of time before he switched over to Geological Survey of India, where he rose to the rank of Deputy Director and Head of Geophysics in the GSI and superannuated there in November 2006. Professor Kayal had his PhD in micro earthquake seismology from the Victoria University of Wellington, New Zealand. And very, very importantly, he is an outstanding personality which integrates the industry and academia and have extensive experience in traveling many countries on academic visits. The list is huge. The countries that he traveled include United Kingdom, US, Russia, New Zealand, Australia, China, Japan, France, Czech Republic, Italy, Germany, Austria, Norway, Mexico, Thailand, Egypt, Sri Lanka, Bangladesh, Singapore, Nepal, Bhutan, Indonesia, and a few other countries. And more importantly, he is leading several international research projects of the Department of Science and Technology. He is a guest faculty to the UNESCO and ICTP, international training courses, a national coordinator, fellow and member of several national and international scientific unions and societies like Indian Geophysical Union, Association of Exploration Geophysicists, American Geophysical Union, International Association of Seismology and Physics of the Earth's Interior, and International Union of Geodesy and Geophysics. He has several awards nationally and internationally, and more importantly, he is a very close mentor and a well-wisher of CSIR NIST, and we have a pleasure of having his mentorship and guidance for all of our scientists and especially for our geoscience department. And on behalf of all the SRTP members, CSIR NIST, and the Geoscience Department of NIST, I thank you very much, sir, for your continuous patronage and guidance over the last several decades to NIST, and we continue to have your support. And I'm very happy that you have accepted our request and then kindly agreed to deliver this talk with a very short notice. And I request you to go ahead. I request Professor J R Kayal.
Thank you, Professor Shastri, for your kind introduction. I am really overwhelmed with your introduction, and now I will try to justify my my assignment today to give lectures on earthquake sciences. And so this is our topic today, earth sciences. I will try to give brief introduction to earth sciences, and then we try to understand how by earth sciences we try to understand earthquakes and tsunamis. So I have tried to organize this lecture for the young students and budding scientists. So I will not go much depth, but I will give some glimpse of the different techniques, how we do record the earthquakes and tsunamis, and how you understand them in terms of our tectonic setting of the country. Now, broadly we can divide our sciences into two major groups in geology and geophysics. But now they call earth science systems, so they also include environmental sciences and geography in this system, earth science systems. Now, among these two major geoscience branches, geology and geophysics, we all know geology is a basic geoscience subject, and it studies the rocks on the surface of the earth, structure on the surface of the earth like faulting, folding, and so on. So geological map is made. Then geophysics has come up as a scientific technology where problems are geological and methods are geophysical, where we try to see the subsurface minerals, oil, gas, groundwater, so on. That is exploration geophysics. Then geophysics also works in the field of engineering geophysics for the dam project, for the nuclear power plant projects, where we do extensive geophysical survey exploration in the terms of bedrock depth and structures, so that the power plant or the dam withstand. Then we have got another branch which is called solid earth geophysics, where we try to understand the interior of the earth, where gravity, magnetic, seismology are the major sciences there. And here today we are mostly in the solid earth geophysics branch of geophysics, where seismology is a great tool to understand the interior of the earth, and particularly the earthquakes and tsunamis for today's lecture. Now there are different institutes where the geology and geophysics are studied. I have given a few names over here: IIT Kharagpur, Bombay, IIT ISM Dhanbad, IIT BHU, Osmania University, Hyderabad, Kurukshetra University, Andhra University, and so on. Now, what is earthquake? The earthquake is when the tectonic stress is much enough, then the rock, the formation or all the rocks, it fractures, and because of that event, the seismic waves, the elastic waves, due to the stress of the rock has fractured, and the seismic waves, which we call the earthquakes, those seismic waves reach to the surface of the ground, and we receive them as a shaking, and we call it earthquakes. So in terms of seismic waves, you are all undergraduate, postgraduate researchers, so I will not go into details, but you all know about the seismic waves, the body waves and surface waves. And in body waves, we have mainly P wave, primary wave, and S wave, CR waves. And in surface wave, we have Rayleigh waves and Love waves. Now these different types of waves due to the earthquakes, we can record in our seismometer or seismograph station, and the record looks like this: the first arrival P wave, then the second arrival S wave, then the surface wave, and so on. So these seismologists' job is to study every wriggle of the seismograms or the earthquake records to understand the earthquakes, how it has occurred and where it has occurred, and all this information they try to extract from these records. Now, as I said, that this is the main tool to understand the interior of the Earth, how seismology or seismic waves has given us the understanding of the interior of the Earth. If we have, broadly, you can, in a pictorial view, you can see that Earth's surface, and then there is Earth's crust, then the mantle, then we have got outer core and inner core. These are the major divisions of the Earth structure, Earth's interior. And broadly, you can see how at different depths these structures, they are also named as lithosphere, asthenosphere, outer core, inner core, and so on. So these Earth structures are understood much by these seismic waves, which is traveling due to the earthquake. The seismic waves is traveling through interior of the Earth, and those seismic waves are recorded. Suppose this is the earthquake occurring over here, and that seismic waves is getting bounced here, coming over here. So all over the Earth's surface, we have the instruments on the Earth's surface, and we get the seismic waves which are coming, following different paths through the mantle, or through the outer core, or through the inner core. So traveling paths also gives us different nomenclature for the seismic waves, which we record, on the stations on the surface. So based on those travel paths, and by ray tracing, we can understand the different discontinuity or different zones in the, say for example, even between mantle and the outer core, we have got the discontinuity, and within that also there are so many transition zones. So each discontinuity is now well imaged by these seismic waves. So they are, say we call it a first discontinuity, call it Moravec discontinuity. Then the discontinuity between mantle and outer core, we call it Gutenberg discontinuity. So these are the major discontinuities, and within that there are several discontinuities we have all imaged at different depth levels. So this is how we know the Earth's interior, Earth structure. Now, what are the instruments that we use to earthquake records, earthquake waves? Now, this is called seismometer. There are different types of seismometers are over here. And this is called seismograph. In our time, there was analog seismograph. Now, since 1980s or so, the digital seismograph has come. So we can record earthquakes by analog recorders. And nowadays, of course, all stations are digital seismograph we have installed. So how we record these? We just keep the instrument seismometer, which is sensing the ground vibration that we keep on the ground, and that vibration comes to the recording panel, and we can record that on a paper, on a smoke paper, or on a white photographic paper, or we can digitize them and record in the digital recording system. So this is the example of how the smoke paper records looks like. You can see the earthquake, P wave and S wave are how they are nicely recorded. And also on the photographic paper, you can also record the seismic waves. And this is possibly example of an teleseismic waves, that is the earthquake has occurred in Iran, and we have recorded in Arunachal Pradesh. So we can record the earthquakes wherever it occurs on the earth, crust, or in the much deeper depth. We record the seismic waves, and this is the digital record how it looks like. The P arrival. This has got three components. The seismic waves has got three components: the vertical component and two horizontal components, north, south, and east, west. So all the three components are nowadays nicely recorded by digital seismograph. And in analog, we can record different component, but for on a different recording system. So now things are more, state-of-the-art techniques has come, and we can record the digital seismogram on a digital system, and we can read them much precisely than the analog seismograms, and we can do much precise work nowadays with the digital system. Now this is the national network, where you can see that 1897 Shillong earthquake was the first earthquake which was recorded by instruments, but not in India. It was recorded by the global stations outside India. And then it was thought that we must have instruments in India. So in 1899, the first instrument was installed in Alipur in Kolkata. Then gradually the stations number increased to 15 numbers sometime in 1960. And then today we have got something like 60 broadband observatory in the national network and more than 100 observatory in different networks. So now the country is well equipped, but previously we had much less number of instruments, but now we have broadband system, digital system, and the country is well covered. And some parts of the country we have got clusters like in Northeast India or in the Himalaya, more close station network is there. So this is now the present scenario of the national network in our country, and these data all go to the IMD. Now it is called NSC, National Center for Seismology. The all data go to the main data center in Delhi. Now, how can we classify different types of earthquakes? Now, there are different types of earthquakes, like tectonic earthquakes. These occur due to collision tectonics of the continents and continents. I will show you the pictures. Then there is subduction tectonics, which cause earthquakes where the oceanic lithosphere goes down along the trenches, and because of the subduction tectonics, we get earthquakes. Then there is divergent or spreading zone earthquakes or transcurrent fault boundary earthquakes. Then there is intraplate earthquakes. So these are all intraplate earthquakes, but there are also intraplate earthquakes, means at the interior of the plate, the tectonic stress is transmitted and we get earthquakes. Then there are volcanic earthquakes that you all know. Then there are induced earthquakes, which are due to reservoir-induced seismicity or nuclear explosion or rock burst or fluid injection in the oil field, in the oil industry, where you inject fluid and you can get micro seismicity and you can understand the oil production planning are made on those, on those observations. Then there are other classifications like teleseismic earthquake, which are much away from your station, say more than 1,000 kilometers away earthquake occur, and you record it at your station, so that can be called teleseismic event. Then there are regional events, depending on the distance. Then there are local events. Then there are nomenclature like earthquake swarm. Suddenly earthquake, number of earthquakes in your area, suppose in Northeast India, suddenly earthquake enhances. Say average 10 events comes in a month. Now you are getting some 50 events in a month, like that of Mizoram could be an earthquake swarm. There could be force shocks. Before a large earthquake, there could be force shocks, and of course there will be aftershocks. Any large earthquake is followed by a lot of aftershocks. And there are other nomenclature like mega earthquake more than magnitude 9, great earthquake more than 8, more than equal to 8, large more than 7, strong we call more than 6, and medium more than 5, small less than 5, and micro earthquakes less than magnitude 3, we call them micro earthquakes. So different types of nomenclatures are there. I'll come to that. Now, what is earthquake magnitude? Earthquake magnitude, most popularly, I think all of us know about the Richter magnitude. Richter magnitude all come in a newspaper, and we are more or less familiar with this scale. Now, Richter in 1934, he was the first seismologist of the world who thought of, to design a scale to know the size of the earthquakes, because earthquakes damage is caused, by the earthquake, and that damage is the intensity of that earthquake. Means an earthquake occurred in Shillong, that may cause total damage in that area, but it may cause little damage or little filling effect in Calcutta. So the intensity is the degree of damage of an earthquake, and that varies from place to place. But earthquake magnitude is the size of the earthquake. To give the earthquake size, how much energy is that earthquake, to know this, Richter first designed the scale, and it is today known as Richter Scale. In 1934, he designed the scale, and it's very interesting. He made some assumption that an earthquake which is occurring at a distance of 100 kilometers with an amplitude of 1 millimeter, it is recorded at a distance of 100 kilometers. That earthquake he has assumed that magnitude is 3. So an earthquake recorded on a wood Anderson seismograph at a distance of 100 kilometers with a amplitude of 1 millimeter, that earthquake he assumed as magnitude 3, and based on that he designed this scale. And it works like a, like a miracle. Means it is now this old scale is compatible with all the modern scale. I will just talk about that. Now this scale, suppose you have got a earthquake, this is P arrival, this is the S arrival. So from this difference of the P arrival and S arrival, you know what is the distance of that, about 8 times. Or by some other means, by epicentral distance. So if you know the distance of that earthquake, and from the record we can know about 8 times of this, suppose the difference is 10 seconds, so that earthquake has occurred at a distance of 80 kilometers from your station. So if you know the S minus P time or distance or S minus P time, and if you know the maximum amplitude, which is over here something like 24 or 23 millimeter, and if you know the this maximum amplitude and S minus P time, so you have the S minus P time or distance, say 20 second is the S minus P time, and 30 millimeter is your amplitude. This is amplitude scale, this is distance scale, and you mark it maximum amplitude and the distance, and you join these 2 points. So that scale will give you the magnitude of the earthquake. So that is it's a wonderful scale he designed, and till to date this scale is it is used. But one limitation is in that scale nowadays we find that it saturates beyond magnitude 6 or so. So nowadays we have different types of magnitude scales, particularly the moment magnitude, which is evolved from mathematically evolved from the waveforms, that is more stable up to magnitude 9 plus. It is much stable. Then there are other scale like body wave magnitude, surface wave magnitude from surface wave, then duration magnitude from the signal duration. You can also estimate magnitude. Then macroseismic. Macroseismic means from the degree of damage, you can also assess the magnitude of the earthquake. So there are different scales. So you people might be wondering why different organization or different seismologists is giving different magnitude for one earthquake. What is this going on? This is, if you mark, you will find that some institute is giving MB, or some institute is giving MW, some are giving Richter magnitude. So different scales. So it depends on the scales. But normally up to magnitude 6, all scales are stable. And maybe beyond magnitude 6, we should rely more on moment magnitude. This is more mathematically, robust scale is nowadays made and it is used. Now, one more important parameter you might have heard, B value. What is B value of earthquakes? Yes, there is a wonderful relation between magnitude of the earthquakes and number of earthquakes. Suppose in Northeast India, in Shillong area, you have a earthquake of magnitude 4, once in a month. Then there will be more number of earthquakes of magnitude, lower magnitude, or magnitude 2, or magnitude 3, or magnitude 1. And what is that? How it goes like a power law. The first Gutenberg and Richter in 1954, they found the global seismicity relation, and they found that if they plot log n, number of earthquakes, cumulative number of earthquakes, and magnitude of the earthquakes, if they plot, they get a good relation, which is linear relation, and that relation is normal value is 1. So that 1 means, since it is in log scale, if your magnitude is 1 down, so that goes by 10 times. So that means a earthquake, so that means the lower magnitude earthquakes are more, it enhanced by 10 times. If a magnitude 5 earthquakes occur once in a month in Shillong, there will be 10 earthquakes of magnitude 4, 100 of magnitude 3, and thousands of magnitude 2, and 10,000 of magnitude 1. So that means lower the magnitude, higher number of earthquakes you can record. So that is actually, this relation has given a tremendous revolution in instrumental seismology. Based on this equation, or based on this relation they found, the instrumental seismology has developed this micro earthquake seismology, so that you can take the micro earthquake instrument to the ground, to the study area for active fault mapping or for purpose of investigation, and you record thousands of lower magnitude earthquakes to understand the fault or to understand the earthquake. So this relation is tremendous, and this is just given one example in Himalaya for Chamoli earthquake, and this can be done by least square method. And nowadays a mathematical formula is given. Maximum likelihood method is log 10e by magnitude bar by magnitude naught, m naught. M naught means the triggering earth means the earthquake. We call it threshold magnitude. Means suppose in your area you have got earthquakes networks such that more than 3 and above you can record all the record and locate all the earthquakes. So 3 is your threshold magnitude of the earthquakes. So that m naught is threshold, means in your catalog what is the threshold magnitude of the bulletin above which the earthquake bulletin is complete. So that we can also find out from this relation. When you plot this data, you will see this line is linear to certain extent. Then it goes asymptotic over here, means from here your data is not complete to have the linear relation. So that magnitude we call threshold magnitudes, up to which the linearity is maintained, and then it goes and gets saturated. So that is m naught. So if you have a bulletin of earthquakes, then you have got you can estimate the threshold magnitude, you can have the average magnitude, and then this relation can give you the B-value. And B-value is a very important seismological parameter in terms of to know the seismicity level there, and to know even it can be used for earthquake precursor studies also. So it is a very important parameter I just mentioned here because it's for all of us to know, particularly for young scientists. Now, the earthquake intensity. Earthquake intensity, as I already explained, it is the degree of damage. So how much, same earthquake has caused total damage in the epicenter area, and it has caused partial damage in the surrounding area far distance, and at a far distance it has been felt. So intensity scales was first designed by Rochefoucauld, and it is something like a descriptive scale where the well-designed house has total collapse. They call it a intensity is 10 or 11, like that. So then the scale, modified Mercalli scale, was then revised in 1956. So you might have heard about the scale, intensity scale. So this is further modified. It is all descriptive. It is given in many textbooks, and including my book also. And then recently came the MSK scale, which is further modified, means further refined the scale, the descriptive scale. Of course, modified Mercalli scale and MSK scale more or less matches, and where modified Mercalli scale goes up to 12, MSK I think goes up to 11 or so. At 11 from 10 actually, if the intensity is 10 means almost total damage. 11 means total devastation. So like that, the intensity scale is designed, and more like Richter scale, scale is more popular till the other day. Now MSK scale has come. Now you have seen the earthquake recording. We have talked about the earthquake magnitude, earthquake intensity. Now how do we locate the earthquakes? It is till the other day, till the computational seismology came or computational methods came, it used to be done by manual method. Suppose your earthquake occur here at some depth, we call it hypocenter, and when you project it on the surface or on the map, we call it epicenter. So, and this is your station. So this distance is called hypocentral distance. So when your earthquake has occurred, say like this, an earthquake has occurred at this station, then this arrival time P and S, this difference gives the 8 times of that difference gives the hypocentral distance. That can be shown by algebraically. So you know at this station your S minus P time, say 10 seconds or 15 seconds. At other station is 20 seconds. At another station is 12 seconds. So at different station, it has been recorded with different S minus P time, depending on the station distance from the earthquake epicenter. So you can draw arcs on the map, taking the, corresponding, S minus P time interval, and you can come out with a center where the arcs, intersects. So that is given as epicenter, and depth. Then you can find out the epicentral distance, and this is h. So h is the depth of the earthquake, and so you can find out the depth also. So these estimate of epicenter and depth, say before 1950 or 1960s, were manually used to be made, and this was the process. But with the invent of computer science, we have now very state-of-the-art techniques to locate earthquakes, like least square method. That is very routine type of location we do immediately by least square method. Then to improve this earthquake location, further improving can be done by joint hypocentral method. This is actually we take account of the station correction at different station is in different geologic formation. So that station correction is incorporated in this technique. So it's called joint hypocentral determination. Then double difference method means we take the difference of time of the earthquake's arrival time and do the computation. So that is more again very precise method, and because it is independent of the velocity model, we are working with the difference of the time interval at different stations. So each station is a PhD topic, so I cannot go into details. So just I am giving you the different techniques that are used nowadays for precise location of the earthquake. Then another very nice method has come, simultaneous inversion. Means in this method, in all the methods, you are giving some, your assumed velocity of the area of that local area. What is the velocity at different layers that you are giving from some constant, some geophysical study or some other information. So based on a given velocity model, these methods are working, but the simultaneous method is working for the earthquake location. At the same time, it is also inverting for the velocity structure. So that means it is simultaneously doing the inversion. It is giving you the location. At the same time, you are giving some velocity model. Now the computer program is taking care of the velocity model structure. So that means we are getting velocity model as well as locations, and that in doing that we get the structural velocity structure, and in terms of velocity perturbation we can image the structure. This is I have given just an example how seismic tomography give us the image of the earth structure. Say this is the Pacific Ocean, the lithosphere Pacific plate is subducting below Japan Trench. So the subducting plate is higher velocity. The blue shows the higher velocity, and this is the lower velocity crust over here, and below the volcanoes the lower velocity, the red is lower, they are much lower velocity. So the crustal heterogeneity is imaged by simultaneous inversion method along with the earthquake location, and that image gives us the picture of the crustal structure. Say this type of structure can be imaged in oil exploration, and they do it much precisely way because they are area is focused area. They made a lot of stations. So and this is regionally we do. So it depends on this scale, at what scale you want the image, the structure. So by seismic tomography today we know the whole earth structure by this method. Now, and that is a wonderful method for also earthquake location, give us the best possible location, because now it is taking care of the earth heterogeneity into the locations for locations. So it is giving you much better location. Yes. Now we have done location. The next important parameter, or say we try to understand the earthquake process, how that earthquake occurred. We now know the epicenter and depth of the earthquake, everything, but how that earthquake occurred, what type of, mechanism of that earthquake. To know that, we can we call it source mechanism or fault plane solution. That can be done by fast motion plot, fast motion solution, or moment tensor. I'll come to that. This is from the waveform inversion, and this is from the fast motion data. Means when this fast motion mechanism by using the fast motion came out from the elastic rebound theory of Reid's elastic rebound theory, which you all might have heard, the elastic rebound theory. It says that when your earth crust is under deformation due to the tectonic stress, say in the Himalaya there is a collision. So because of the tectonic stress, your earth crust is under deformation, and you can see due to tectonic stress, the earth crust formation is under deformation, and then at certain stress, when the elastic limit exceeds, then the structure breaks, and that is earthquake. So when that breaks, when that fault occurs, we call it fault, in geologically call it fault. When that fault occurs, the ground movement is like this. This side goes this way and this side goes that way. So that ground motions, at different quadrants, we can imagine another orthogonal quadrant, and you can see that at different quadrants, the ground motion is different. Somewhere it has come up motion of the seismic wave, that P wave has come at up motion. When you get a boom sound of the building, that has come either up or you have gone just feeling down. So that up motion or down motion of the seismic waves or the first arrival is due to this ground motion, and that is recorded by our seismogram. Our seismogram records the first motion, how the wave has come, first have gone up or down. So that up motion and down motion of the ground movement can be plotted by a geological technique. We call it stereo net plotting. That I cannot explain it. This whole slide will take 1 hour lecture for the students, but just you try to get some glimpse how the seismologists do the focal mechanism. So from the fast motion we do plot this data on a stereo net, how the motion has come at this station up or down, and that station with respect to epicenter, what is the azimuth. So if we know the azimuth and the angle at which the ray path has come, that we all compute in the computer methods. So if we know the angle of incidence, how it is coming, and the azimuth of that earthquake, so we can plot it on a stereo net. That is geological technique we take, and we plot them, and then we draw two nodal planes like here, two nodal planes we draw here, and we try to find out what type of solution it is. And normally for thrust faulting, when your rock is under compressional stress, we call it under compressional stress, then you get thrust faulting. So that thrust faulting due to dominant compressional stress, horizontal compressional stress, will give a thrust faulting, and that is a symbolic representation of thrust faulting. When your region or your rock is under tensional stress, then it breaks and it gives a normal faulting. I'll come to that. So we get this type of motion. Means the white part shows directional motion. As I said, when the ground moves this side, this is compressional motion, and that side directional motion. So that is the down motion, up or down. Up is compressional motion of the ground, and down is the directional motion. So based on these plots, we come out with the fault plane solution, either thrust faulting or normal faulting or style-slip faulting. Just you take it from me how different types of faulting we try to understand from the earthquakes. What are the techniques seismologists use, and then what are the symbols we use to denote this is thrust faulting. This is thrust faulting with some components. There is thrust faulting, but there is some style-slip component in that. Then this is normal faulting. This is, if you can see this one, this beach ball is pure normal faulting. This beach ball is showing pure thrust faulting, and this beach ball is showing pure style-slip faulting. So different types of solution will come out, and we try to understand how that earthquake occurs by thrust faulting or normal faulting or style-slip faulting, like that. And apart from that, you can also do the, nowadays with the waveform inversion, we can also come out with a solution by waveform matching, means the actual waveform recorded and the synthetic waveform based on our model, and we come out with a fault plane solution. It is not seen here. I think you can see it. So this is the fault plane solution of one earthquake we have recorded in Dhanbad, observatory, and from a single station data we can also do this, waveform immersion. By waveform immersion we can also get the fault plane solution. This is strike slip faulting earthquake. So by these different types of, by fast motion plot, manual plot, or nowadays it can be plotted by computer, we can do the fault plane solution from the fast motion data, or we can do from the waveform inversion the fault plane solution. We call it moment tensor solution. Now I think we have done this. Yeah. Sometimes it's stuck. Yes. Yes, I think. Yeah. Now let us come to, I think I am running out of time, different plate. So you can see the whole Pacific plate is spreading, from the spreading ridge is moving and subducting at different, Aleutian Trench, Japan Trench, Philippine Trench, Ugongi Trench, and subducting, and where it is Indian plate from the Carlsberg is moving towards north, and it is colliding with the. So here we get collision tectonics, as we call collision earthquakes, tectonic earthquakes, and the subduction tectonic earthquakes. And also in the South American plate, Najaga plate is subducting. I think I have to go fast now. Now this is the picture how the plate movement, today's Indian plate how it has come to with the head-on collision with the Eurasian plate over here, and this is the topographical structure, and where the Indian plate is moving to the north and on head-on collision over here, and the Himalayas has come up. Here the oceanic Indian plate is subducting along this Java, Sumatra, Andaman Trench, and also we are getting subduction tectonic earthquakes over here and collision tectonic earthquake in the north in the Himalayan belt, and also in the northeastern region. This belt is connected with the subduction zone. We are also getting a lot of earthquakes in the northeast India. So this is the pictorial view of how we are getting collision tectonic earthquakes, and this is subduction tectonic earthquakes. And in subduction we get volcanic arc. We have got a trench along the large earthquakes and the great earthquakes. You can see that there are so many great earthquakes. The stage start like 1950, 1897, 1934, 1905 Kangra. So there are many great earthquakes, several great earthquakes, and many large earthquakes. And in Northeast India, you can see it's about 2 dozen, large earthquakes and 2 great earthquakes, 1950 and 1897. But within the plate, we call it intraplate earthquakes. This tectonic stress is transmitted to the intraplate region. We have got this 1993 Kilari earthquake, 1997 Jabalpur earthquake, 1967 the Koyna earthquake, and here in Bhuj also we get many earthquakes here, and 2 large earthquakes in the recent years. One was that 2001 7.7, and there was also a 1956 a strong earthquake. So this area also you get a lot of earthquakes here. And if we see that now the beach balls. Now in the intraplate region we have got Koyna earthquake by strike slip mechanism. We have got Kilari earthquake. Now each earthquake is a 1 hour lecture. So I just give you the glimpse how we see the earthquakes in the intraplate region, and in the Bhadrachalam and Ongole we have got strike slip earthquakes, strike slip component. In Midnapur also we have got this thrust faulting with strike slip component. In Jabalpur this is also the thrust faulting with strike slip component. So like that in the intraplate region we get mostly by reverse faulting or by pure thrust faulting, and reverse faulting with strike slip component. So these are the earthquakes, different earthquakes in the interpret region recently. And in the Himalaya, we see the Himalayan seismic belt, which is between the earthquakes between the main boundary thrust, we call it, and main central thrust. Between these 2 zones, all the earthquakes are called Himalayan seismic belt earthquakes, and earthquakes mostly occurred in this belt. And all the earthquakes in this Himalaya are by thrust faulting mechanism. And beyond that, in the Tibet area, we get earthquakes in normal faulting mechanism. So this is the scenario in Himalayan earthquakes, and this is the scenario in the peninsular India region. And if you see the Himalayan tectonic, model, they say that Indian plate is gently dipping, and it dips very gently, and the below MCT, main central, below the Himalayan seismic belt, the depth is of the order of 20 to 25 kilometer, and all earthquakes are shallow over here. And you can see the actual data over here. The earthquakes are mostly shallow along, they call it plane of detachment, that is the basement, Indian basement. This is the boundary, and along over this all the earthquakes are occurring. But nowadays we are finding with close network in Nepal by France Nepal collaboration, we are also getting some deeper earthquakes. So there is a bimodal seismicity, but most of the earthquakes are above plane of detachment, or that we call it Himalayan main thrust, or main Himalayan thrust, MHT. And the great earthquakes and large 1988 earthquakes could be deeper, or it could be, there is a controversy, so it could be also on this basement thrust. So this is the Himalayan earthquake scenario, and most recently that Nepal earthquake occurred, and this is the rupture zone, 1950 rupture zone of the earthquakes, Assam earthquake. This is the rupture zone of the 1897 Shillong earthquake. This is the rupture zone of the 1934 Bihar Nepal great earthquake, magnitude 8 or 8.3, and the Nepal earthquake 7.8. This red, so the rupture of the Nepal earthquake. Now this is the rupture zone of the 1905 Kangra great earthquake, and in between there is a gap, and people say that this gap area may cause a large earthquake. Now if we come to the northeast India and the Sumatra subduction zone, this Indo-Burma range, and it is connected with the Andaman Sumatra Java trench. And if you do the sections of these earthquakes, you find that below Indo-Burma ranges earthquakes are down to 200 kilometers along this section, and along the Sumatra it is down to 350 kilometers, and along this further south, further here it is down to 500, and in the Java region it is down to 660 kilometers. That means this is called Bvalue zone. The subducting lithosphere going down, and the earthquakes within that lithosphere, we call it the seismic zone or Bvalue zone. So means from this seismicity structure, from this seismicity observations, we know how the subduction structure is going, how long, how much deep it is going, and you can see that below Indo-Burma ranges it is down to 200, and then below Java it is down to about 700 kilometer depth. Now this is the recent earthquakes. I think you all know how it happened, but the details you will get in my book. And now this is the maximum intensity was of the order of 10, means total collapse in this red part, and then the intensity was 8, intensity was 7, like that. So 8 means partial damage and 7 means little bit crack and all. So this is the intensity map of that Bhuj earthquake, and this is the in the total damage area. The good buildings has totally collapsed, and also the surface, the sand was shallow and water table was shallow. So that liquefied, and many structures has gone down. So this is called liquefaction. That was the scenario of the Bhuj earthquake, and this is the scenario of the 2004 Sumatra tsunami earthquake, where total damage was in the Nicobar Island, and the jetty were totally damaged, and how the people were panicked in Thailand to run away. Now this is an interesting picture. You can see the earthquake occurred in the Niwas Island in near Sumatra, and is about 1300 kilometers in Andaman. In Baratang, we have seen that earthquake, by the earthquake, a big tree, the trunk was, splitted, and it was separated by about 4 feet. So this is a spectacular picture, how that earthquake, that shaking has come about 1300 kilometers away, and the trees, and the many, and the liquefaction, and the mud and volcano was there, erupted, and then the damage in the Little Andaman Island. So this earthquake was, mega earthquake, and a 9 magnitude earthquake is equivalent to about, 33 magnitude 8 earthquakes at a time. The earthquake energy goes, in power law, about 33 times. So a 9 magnitude earthquake means 1.8 magnitude earthquake. You know about that 1950 Assam earthquake or 1897 Shillong earthquake, and 9 magnitude means 30 or 33 earthquakes of magnitude 8 at one time. So that was the energy released by that mega earthquake, and that was the scenario about 1500 kilometers away. Now there was crustal deformation. The GPS stations found that there is a movement of the ground by few centimeters horizontally and also vertically. So there are many observations of these Sumatra earthquake. This is in the Andaman Island, how the ground deformation was measured by the GPS stations. Now these seismologists talk about earthquakes, but can they predict earthquakes? No. The simple answer is no. Till today we can't predict earthquakes, but we try to understand the earthquake's precursor. Sometimes we get stuck. Yes. So we did some earthquake precursor studies from GSI. We tried to see the Earth's resistivity changes before a felt or large earthquakes. We tried to see the seismicity rate. We tried to see the velocity changes or gravity changes. We got some anomaly, but yes, it is good to understand how the things are changing, but it is difficult to predict earthquakes based on these observations. And at least till today, we can't predict earthquakes. But what I want to tell you that earthquake precursors are observed for some earthquakes, not for all earthquakes, but sometimes they give good signals, sometimes they don't. And like sometimes the animals behave anomalously, sometimes they don't. So in Shillong area, we were observing Earth's resistivity at two stations, at two different formations. One is phyllite, one is granite over here. And these are the electrode separation by about 1 kilometer and distance was 3 kilometers. And at one formation, this granite hard rock formation, we found that there are changes in resistivity before a large earthquake, a Kachar earthquake, and other stations had no change. Whereas in the phyllite formation, all the direction we are measuring in different directions. All the direction has shown change in the resistivity. So we find that the earthquake resistivity, Earth's resistivity may change or may not change depending on the measurement direction, depending on the rock formation. And we found this type of observation before the Kachar 5.8 earthquake, about 70 kilometers away from our observing stations. Now this is also before the Kachar earthquake. We had micro earthquake networks, but there are some break in data. The networks were run for 6 months every field season. So you can see that though there is a gap of data, you can see that they see the normal seismicity, say something like 15 or so earthquakes per month or whatever, and then the earthquake suddenly increased. So and then there is of course there is no data. Then there was an earthquake over here, somewhere here, and then again normal seismicity came. So the seismicity rate also changes. We also try to see the velocity ratio of the ground, and we found that before the Kachar earthquake, there was a change in velocity. And we also try to see the gravity changes, and this is of course in Sikkim, Himalaya, we try to observe the gravity value, repeat gravity observations at the fixed stations, and we found that before the earthquake of magnitude 5.7 in Sikkim, there was a lowering of gravity value. So these are the observations we have made, but we are unable to predict with these observations where and when and what magnitude earthquake will occur. Time, space, and magnitude. We cannot say now. Now, then what best we can do for the society? We can give them a seismic hazard zoning map. And it is a very familiar map. This is the old map, this is the recent map. You can see that Northeast India, whole Northeast India is the zone 5, or that is of the order of 0.36 G value. Zone 5 means about 0.4 G. Zone 4 means about 0.3 G. Acceleration of the ground can happen. So these are the zonation map. Most vulnerable zone is Northeast India and some parts of the Himalaya. And then there are zone 3, zone 4, and zone 2. So zone 2 means 0.1 G. So different zoning map has been made, and based on that, there is a building code. So if we make our buildings according to the building code in different zones, possibly we can make a earthquake resilient society. So this is a broad zoning map, but we can also give the society the microgeneration map, seismic hazard microgeneration. How we can give you? Suppose there is also a side response. Side response means suppose I blow on your body, on your shoulder, you will not get much pain. But if I blow on your nose, you will get much pain. Why? Your body is sensitive at different parts of your body. Similarly, Earth's different parts has got different sensitivity. So in your area, you can see some area the total damage has occurred. That's what we have observed in Jabalpur case, and so this is the case. So suppose this earthquake has occurred, and this is the hard rock, and there is a charge, and the seismic waves is hitting this building, and same building here, but it is the seismic wave is passing through the sediments, and that seismic wave is getting amplified in sediments in loose formation, and it is shaking or breaking the structure. So that we call side response. So where you are making the say nuclear power plant or dam or anything, or a multi-story building, or you are making a urban design, making. So you must know, you must have the microgeneration map, and that seismologists give based on the side response study. Say in different formation, the seismic waves has got different amplification. So based on these observations, we can give you microgeneration map, and that's what we have produced for the Guwahati city based on the geology, geomorphology, based on ground basement tomography, means how we can do the resistivity survey and know the ground, what is the depth of the sediments, and we can do, and also we can study the landslides, and also site classification and site response, that what I told you just now, at what frequency the site is getting amplified, the seismic wave is getting amplified. So all this data, and the PGA value also, at what is the maximum acceleration you can get in that site. So all these data or observations or map are on GIS platform. We produce the microgeneration map of different cities, and that is a mandate of MOES to make microgeneration map for all the cities in the country. And so we have produced, scientists has given you the microgeneration map. So these are the most vulnerable zones in Guwahati city, where your buildings should take the engineering design so that it can withstand the earthquake shaking. So this is the map we can produce, and it is the administration which has to implement this scientific data for the urban planning. You see, all the old buildings in Japan, they take lessons from their earthquakes. The old buildings before the 1980 made, the old buildings are retrofitted, and the new buildings are earthquake resistant resilient structure. This is a bush here, and the whole building will swing, it will not collapse. So that is the new building design in Japan, and this is the old building, all are retrofitted. And you can see how lessons they take it. You can see, if you can see this carefully, the rock has, this is actual picture of that area when the Kobe earthquake occurred. The thrust faulting, you can see that formation has gone up. You can see this is the textbook type of picture how the thrust faulting has occurred. This has gone up, and this is kept as a museum in that area. And also the damage in a house is kept as a museum in that area for the next generation to see what happened in the Kobe earthquake. And just another one, 4-5 May, tsunamis in India. These are the two zones where from we can expect tsunami, from the Makran subduction zone and from the Andaman Sumatra subduction zone, where from we get the tsunamis. Now this is the historical data which says that 1945 there was a tsunami in this part of the Makran due to Makran earthquake, and there was another earthquake in 1947. So there are two cases of there is some debate on this. There are two cases of tsunamis from the Makran subduction zone, and we all know about this subduction zone. This 2004 Sumatra earthquake, how it has fractured. This green symbol is showing the fractured zones, how it has fractured something like 1,500 kilometers down to Andaman Island, and all along this fracture. And this tsunami was hit in the eastern coast of India. So this part we all have experienced, and you can see how the tsunami has reached from the Andaman Sumatra zone, this earthquake has caused, and this tsunami is hitting the eastern coast of the India, and also it has reached to African. And so this is what we have experienced about for the tsunami. You have got three conditions. The earthquake has to occur in the sea and at a shallow depth, means at the subducting, upper in the subducting lithosphere, and by thrust faulting mechanism. If it is by strike slip faulting mechanism, tsunami may not be generated. But if it is by thrust faulting, the water column is thrusted off, and that thrusted up water column in the middle of the sea, reaches to the coast as a tsunami. So that is what is the experience of 2004 Sumatra tsunami. And today we have, this is last slide. Today we have got the, yes, tsunami we have got enough time to do the tsunami warning, because our Indian East Coast, our tsunami zone is Sumatra Andaman subduction zone, and from there, if any earthquake cause tsunami, we have got about 2 to 3 hours for the tsunami to reach to our Indian eastern coast. So by that time, within 10-15 minutes nowadays, we can, from the telemetric network, we get the earthquake data and get the earthquake magnitude and location. If it is in the sea and it is shallow, magnitude 8. And if it is within another 5-10 minutes, we can find the mechanism of the earthquake. And if it is by thrust faulting, we can do the warning. It has happened 2008 earthquake. They first warned the tsunami, then they found that the earthquake was of strike slip faulting in the Indian Ocean. Then they withdraw the tsunami warning. So we are in a better place. In a sense, Japan is within 30 minutes, 20 to 30 minutes, they get the tsunami, or maybe less than that sometimes. But Indian coast is far away from the tsunami zone, and nowadays we have got the warning system, and they are working very well to warn the tsunami before it reaches to the coast. Thank you so much. I think I have overstood the time. Very sorry for that. So thank you so much for your present listening. And I think now I can take up your any questions. Yes.
Thank you, sir, for the elaborate lecture. So for the question answer session, may I request Ms. Monty Gogoi to take over? Yeah, Monty can take the questions, sir. There will be many questions from across all the platforms, that is Facebook, yes, YouTube, which Monty has compiled, and she will ask. So Monty, please.
Thank you, sir. On behalf of our director and the entire SRTP team, we thank you, sir, for your such an elaborate, insightful presentation. It was indeed a great pleasure for all of us to listen to you, sir. And we could not agree more on how nicely you have presented throughout the presentation. No wonder, sir, all the live platforms are filled with appreciation remarks, which includes from MS Team, YouTube, and Facebook. Sir, and there are a lot of questions. With your permission, we would like to begin question and answer session. Should we, sir?
Yeah. My pleasure. I'll try to answer if I know. Yes.
Thank you so much, sir.
Thank you.
Sir, we have the first question from Sneha. In future, what advanced technology can be brought in seismometer?
Well, I think at present broadband, I think in our time, 3-component digital seismometer came. Now the broadband system has come, and there are different type of seismometer, of course, and I think it is instrumental seismology, discipline. They can answer, or they can tell what new advancement is coming. But with the present advancement, with the broadband seismometer, we can work well. This much I can say. And in with ordinary 3-component digital seismometer, we were limited with the frequency range. But with the broadband seismometer, we are, I think, much comfortable. We can study seismic waves of different frequency range. I think it is working. So far, it is working very well. And maybe the instrumental seismology will go much further advancement and bring out a much better seismometer in future.
Thank you, sir.
Yeah.
Sir, the next question is from Prabhakar Kumar. He says, how is the stress accumulated in intraplate earthquake? Is the stress in case of intraplate earthquake transferred from the interplate region?
Yes, it's a very good question. I think it is yes. The answer is yes. You know, say for example, in the middle of the Indian Shield, the Kilari area, and which is thought to be very stable land and no earthquakes for hundreds of years. And then you got the earthquake, 1933 earthquake. Now, studying this earthquake, we can see that the tectonic stress in this region was compatible with the plate motion, means in the northeast direction. So we suppose that the tectonic stress, which is due to the collision tectonics at the Himalaya, that tectonic stress is maximum there definitely, but that tectonic stress, not south or northeast, southwest, that tectonic stress is transmitted to the interplate region, and in the interplate region, any fault zone, if it is there, that fault zone is accumulating the stress and it is getting activated. Say the paleoseismological studies shows that in the Kilari area, there was a earthquake about 1,000 years ago of similar magnitude. Now that fault, has been activated in 1993 earthquake. So yes, the answer is yes. It is from the collision zone, the tectonic stress is transmitted to the interplate zone. Yes.
Thank you so much, sir, for patiently answering. The next question is from Anusha Yadav. Sir, why are new faults occurring in Nepal, and what does the Himalayan seismology shift there indicate?
Please tell again, speak again.
Why are new faults occurring in Nepal, and what does the Himalayan seismology shift there indicate?
I don't know what you mean by new fault. Now, maybe you see whether the fault is causing earthquakes or earthquake is causing fault, that's another debatable things. But the way we understand in the Himalaya, in the whole of Himalaya, the Indian plate is gently dipping, and that interface or the basement of the Indian interface of the Indian plate is called plane of detachment, or is called main Himalayan thrust, MHT. So it is the MHT which is getting rather stress getting accumulated, and on the MHT the earthquake is occurring, and that is triggering the existing fault or creating new fault. Means if I had the time, I could have shown you the Chamoli earthquake. We have investigated from GSI, Chamoli 1999 Chamoli earthquake. We have seen that all the aftershocks and the main shock 1990 Chamoli earthquake. You can see my publications, or you can see my book, that 2008 Springer book. So the Chamoli earthquake occurred on the MHT, on the that basement thrust, and that earthquake has triggered the Alagnanda fault. You can say Alagnanda fault is a new fault has been created, or it was the existing fault and that has been triggered. And the geologist has, when our geologist mapped that area, they found that Alagnanda river they named it Alagnanda fault, and we found that Alagnanda fault, if we extend to the MHT, we can find that at the Alagnanda fault, you can see in my publication or in my book, that at the Alagnanda fault 10, where it is ending on the MHT, on the basement thrust, the Alagnanda fault is ending on the MHT, and at that ending point, the tectonic stress is accumulated, and that main earthquake, main shock occurred there at the end of the Alagnanda fault on the MHT, and that earthquake triggered the Alagnanda fault to generate lot of aftershocks on both sides of the Alagnanda fault. You can see my publication. So you can say the Alagnanda fault is a new fault. So what I would like to say, that it is the MHT which is generating the main shock, and that shock is triggering some existing fault or creating new faults. So it is not that, in Nepal some new faults are getting created and then the earthquakes occur. I would say on the other way around, that on the MHT the stress is accumulated because of the tectonic collision, and that stress is getting released on the MHT thrust, and that stress release or that great earthquake is activating the existing fault or creating the new fault. That way I will explain your question.
Thank you, sir. So the next question is, what is the depth uncertainty associated with the catalog data of earthquake?
Oh, yes.
How accurately can it predict the depth of earthquake?
No question to predict anyway. So yes, who are working with the catalog data, I would advise them to be bit careful, in the catalog, particularly the old catalogs before 1964, because since 1964 we have got global network. Then nowadays we have got very good global network. We call it GSM network. So data since 1964 are better, but before 1964, when the global network was not there, those data, those depth of the earthquakes are maybe erroneous, much erroneous. But even with this global network data, I always advise my students or researchers to go with the EHB data. Means within the International Seismological Center catalog, there is much precise location is given by the EHB catalog. Means there are some scientists, he is Ingdahl, one of my good friend, one American friend, seismologist, very famous. They have relocate the, as I said in my earthquake location, that by least square method you locate the earthquakes. But when you do PhD or for research, then you go for double difference method or seismic tomography method to simultaneous inversion method for much precise. So routine location has got, nowadays the routine location, even the routine location has got depth error. But when you take the EHB catalog data, the depth is better estimated in the EHB catalog. So if you work with the catalog data, with the seismological bulletin data, I would advise you to study the earthquakes which are located by the EHB or the EHB catalog data. So earthquake depth has got lot of error before 1964, and after 1964 the network is better, but even then don't use the routine bulletin data, use the much refined data, that is EHB catalog. Thank you.
Thank you so much, sir. Sir, if you have time, sir, can we proceed with the last question?
Oh, please, I have time.
Thank you so much, sir. Sir, what are the precursors seen before the occurrence of large earthquake?
Yes, it's a full lecture and it's a good question. I appreciate your interest. You see, there are various types of precursors observed all over the world. In 1980s, the precursor studies were in peak, and people thought that they can predict earthquakes. So there are geophysical precursors, there are geochemical precursors, there are geological precursors. So many types of precursors were monitored. In geophysical precursors, say the gravity of that region changes due to big mass transfer. The gravity value changes. The magnetic value also changes in that area. The resistivity value changes. So a lot of geophysical precursors are studied. Then seismological precursors, as I just very quickly I mentioned about our study in Shillong area. The seismological precursors are the rate of seismicity suddenly changes, the B value suddenly changes, the velocity of the earth structure changes. So there are many seismological precursors that you can study. Many geophysical precursors like gravity, magnetic, resistivity you can study. Geological means geomorphological, you can study the water level depth, means in the water table depth, say in the dark well, or the spring water discharge, how whether it changes before earthquake, it changes. So, and then the geochemical means the radon content of water or soil changes. So, lot of case histories are there. Before a large earthquake, we have got many type of precursors, including in GSI we studied some, and also NEIST, CSIR NEIST also has developed from MOES. They have developed a GMPO, multi-parameter geophysical studies, observatories. So they are also studying different kinds of precursors. So yes, we are trying to understand the precursors in terms of large earthquakes, but as of now, I would say that let the precursor study goes on. We definitely increase our knowledge how the physical parameters changing before a large earthquake or after a large earthquake. That's fine. That's good for research publication or for understanding. But as of now, I suppose we are not getting any successful prediction except 1975 Haichang earthquake. The Chinese seismologists, geophysicists, seismologists, they had a lot of precursors, observations. And unlike in India, where everybody and anybody predict earthquakes, including astrologer, in China, a scientist cannot predict earthquake. All observations goes to earthquake prediction committee, and the prediction committee is authorized to predict earthquake. So when the Chinese seismologists, geophysicists, and geologists, they gave a lot of precursors anomaly, sent a lot of precursor anomaly happening, abnormal anomaly. As I said, resistivity may change, and water spring discharge may change, radon content may change. All these observations were sent to the prediction authority, and they were in dilemma what to do. It is something really, scientists are saying something happening. So what we can do about it? But they don't know, we don't know when and where and what magnitude will occur. Then suddenly, one fine morning, they found all snakes, rats, and all things from the underground. It was abnormally on the surface of the ground. The roads are difficult, to walk, or it was abnormal behavior of the animals. Then the prediction committee, based on the scientific data and based on this animal behavior, abnormal animal behavior, they announced on TV and radio that you come out from your house within 24 hours or within few hours, and there could be anything. Something wrong is there, so you all come out from the house. So they all came out from the houses, and they were in the tents or on the ground or whatever. And within 24 hours, next day, the earthquake occurred. So they saved the lives. Millions of lives are saved by that. That is the only successful prediction, you can say, official prediction of earthquake, by which the human lives were saved, but the properties were not saved. Naturally, the whole city were destroyed. But in the same country, in 1976, the Tangshan earthquake, a bigger magnitude 7.6 occurred, and the whole city was destroyed. So, but Chinese still believe that they can predict earthquake. They are still on the job. But all developed countries, including Japan, USA, and all countries, even in India, we have come to the ground truth that we must go for the microjonation, and we must build our earthquake resilient houses to survive. That is what Japan has done. So I think microjonation map, seismic hazard map is of more practical use to give a earthquake resilient society, or to develop an earthquake resilient society. And earthquake precursor, I don't say that it is impossible, but I say as of today, we have not been successful to predict earthquakes with time, with space, particular place, and with magnitude, what magnitude. We can identify the defined earthquake vulnerable regions where the next earthquake may come. That we can identify, but we can't say when and where and what time it will come. So I think we should, for all practical purposes, we should go for the microgeneration map and precursor study. Let it be a research for future earthquake, prediction. So that is my personal view. Yeah.
Thank you so much, sir, for patiently answering all the questions. We have a stream of questions, sir, and we'll be compiling all the questions and sending it to you, sir. Sir, we are really enlightened to hear your lecture, and we feel really fortunate enough. So your talk started from the very basics of seismology and took us to the various fields, and we really feel overwhelmed to hear from you. There are a stream of, like, sir, a lot of appreciation comments also, sir, that your lecture was so informative and so, sir, enlightening. Thank you so much, sir.
Thank you so much. It's my great pleasure. It's my great pleasure. Thank you so much for inviting me to such forum. I really enjoyed it. I always enjoy, lecturing. So it was my great pleasure. And I thank all the participants for their patience hearing. And thank you, ma'am, for your kind, comprehension of the, ending session. Thank you so much. And thanks to the director. Thanks to Professor Shastri for inviting me and for giving me this opportunity for this interaction and for this forum. Thank you so much. Thank you all.
Thank you very much. Before we can say vote of thanks, Dr. Saurabh Barua, would you like to say something?
Yeah, thank you for giving me this opportunity. Yes, I am very much happy to see the deliberations by Professor Kayal. And before vote of thanks, actually, I would like to mention that Sir is associating with us maybe last 3 decades in CSIR Northeast Institute of Science and Technology, and he has imparted lot of guidance to all of us. And what lucidly he has delivered the lecture, that was really extremely learning lessons for all of us, maybe particularly myself. So in this regard, just I would like to say thank you so much, sir. And you have concluded well within our aspirations, and our students, SRTP students, are really motivated, and they are really blessed by your lecture. Thank you so much, sir. That's
Thank you so much, Saurabh. Thank you so much. Thank you. I love you.
Thank you, sir.
Thank you.
Over to,
yeah. Sir, our student has made one slide summary of your talk, and it is shared on your screen. Can you see, sir? Is it visible to you, sir?
Can you please repeat your what you said?
Yeah, your talk is summarized in one slide, and it is shared on your screen. Can you see it now? Sir, this summary slide will be shared with you also.
Okay, it's fine. It's fine. It's okay. Fine. Thank you so much. You have done a good job. Thank you.
Our SRTP team has thoroughly understood your lecture, and they have summarized entire thing out of your lecture, and they've portrayed in front of you what you have delivered.
Thank you so much. Yes.
Thank you.
Thank you. So nice.
Over to.
Thank you, sir, for your lecture and this insightful talk. And now I request Mr. Ravi Kumar Lingam to propose vote of thanks.
Ravi, you have to unmute. Ravi Lingam, you have to unmute.
Oh, sorry. It's my privilege to propose vote of thanks on this occasion. I, on behalf of Director CSIR NIST and the entire SRTP team, and on my own behalf, extend very hard thanks to Professor J R Kayal for sharing important topic, earth sciences, earthquakes and tsunamis in India. A big thank you for you, sir, for enlightening us with your lucid presentation. So you have covered the basics of this seismology and earthquake related the basics. So and also this how we can identify the epicenter and the manual methods and the computational methods and the source mechanism, how these earthquakes happen, and the plate boundaries, and especially this Indian plate motion, and the great earthquakes that happened in India, and especially this earthquakes prediction precursors and seismic hazard zoning maps of India, and the microgeneration maps, especially for Guwahati city. Thank you very much. And finally, this tsunamis in India. And you covered 2004 Sumatra earthquake tsunami and tsunami warning systems. So thank you very much, sir. I thank you all participants who has joined through MS Team, YouTube Live and Facebook Live. And I profusely thank Dr. G. Narahari Sastry, Director CSIR NIST, for guidance and motivation. Thank you all. Jai Hind.
Thank you. Thank you so much. Thank you. Thank you all. Thank you.